boa tarde. Então vamos começar, né, mais um seminário de Lolita, né? Essa semana então foi a acústica na terça-feira, agora o Frank vai falar. O Frank é colombiano, mas ele trabalha na França, na École Polytechnique, CNRS, e ele também é professor na Colômbia. Tem dois jobs, né? Dois empregos. E a área do Frank é teoria da concorrência e ele é do grupo de pesquisa da gente lá na França, certo? Então,
thank you very much. So I'm going to give you a brief introduction to the theory of concurrency. And I was wondering if I gave this talk in Spanish, would you understand me? Si doy la introducción a la teoría de la concurrencia, do you understand? No. I'll give it. I could give it in Spanish, but the terminology we don't have it in Spanish, so we have to do this. But you can, please feel free to ask any question. This is not like a talk; it's more like a class. So you can raise your hand, ask questions, and Portuguese is okay. You just speak slowly. Okay, so concurrency is the study of concurrent systems. So concurrent systems are, you have multiple agents that are interacting with each other, right? So we are familiar with them, reactive systems, systems that react continuously with the environment, like when you are interacting with the browser, for example, is reacting to your input. Synchronous systems like telephones, you synchronize with the person talking. Mobile systems that you're moving. Secure systems where you care about security. And biological systems. They are all part of concurrent systems. And they can combine. And the best example of that is the internet. The internet is this very complex, huge concurrent system. So the models of concurrency, what they do is they formalize this. They try to describe, analyze concurrent systems. Are like tools to be able to predict the behavior. Just like you have theories in physics to predict certain physical behaviors, this is the same, but for concurrent systems. So typically these models, they need to be simple, because it's too complicated, people will not care to learn it. Must be expressive, meaning that it should capture certain phenomena that from the real world. It should be able to express interesting phenomena. It should be formal, and that means being founded upon mathematics. And it should provide reasoning techniques, meaning that it should provide ways to predict behavior, to reason about the phenomena you are trying to model. The models that we're going to see here can be thought of as being the Lambda calculus for sequential computation. Which one of you is familiar with Lambda calculus? No? More or less? Okay. So it's the Lambda calculus of sequential computation. You don't need this. So what's the problem with the concurrent systems? Is that the traditional models that you know for sequential computation do no longer apply. Because, I mean, typically when you learn how to program or you are doing some algorithms, you're typically interested in things that terminate, right? Termination is a very important aspect of an algorithm. Here, most systems actually, they do not terminate. Like a browser, for example, is running forever. They are reactive. It's not like the algorithm that you get an input and it produces an output. These are interactive. They are continuously getting input from the environment and producing partial outputs. And they are non-deterministic, so that means they are unpredictable, or there is some degree of unpredictability. So I've been saying this for 10 years, so it's not longer. It's not a new area, but it's not totally mature area. So unfortunately, in concurrency theory, there is not like the canonical model in which everything can be expressed. No, it's rather like there are several models, each one focusing one particular aspect of concurrency. because concurrency is such a broad area, so there is a model for synchronous communication, a model for mobile communication. So no canonical model yet. There are two kinds. One is the process calculi, which are the lambda calculus of concurrency. And one particular one is CCS, the calculus synchronous communication, and the pi calculus. Those are probably the most significant calculus for concurrency. And the creator of this calculus is Robin Milner, which is a Turing Award that died 7 years ago. And these are syntactic models of concurrency. So basically, they have terms like you're familiar with regular languages, context-free grammars. They are in this linguistic part of computation. So basically, they have rules like this. Say, like, if you have a P that evolves into P prime, the parallel composition of P and Q also evolves into P prime parallel Q. That would be a typical operational rule. And another kind are the ones that they look like automata. Are you familiar with automata theory? So these are like automatas for describing synchronized change, concurrent change. And probably the most popular ones are Petri nets. So, and process calculus have been applied widely for modeling biological systems, correctness of distributed algorithms, analysis of object-oriented programs, modeling business processes, and I could go on forever. So I'm going to give only a brief introduction to some aspects of these calculi. So I'm going to start from computability. Are you familiar with computability, decidability, and all these things? Okay, that's perfect. So you know, an automaton have a set of states. Some of them are initial, some of them are accepting, and a transition that tells me how to move from one state into another, right? So can somebody tell me what the language of that automaton? Just to make sure that we are speaking the same language. Yes, so, but what language, what sequences of strings that this automaton recognizes? Or is the sequence 1, 0 accepted by this automaton? No. Okay, so, but the sequence 1, 0, 1 is accepted. Yes. Okay, so basically, the automaton accepts this string if there is a path from the initial state to a final state labeled by the string. Okay, and the language is the set of all strings that are recognized or accepted by this automaton. And regular languages are the languages that are recognized or accepted by finite state automata. And they have the same expressive power than regular expressions. So for the previous automata, the regular expression would be, this could be a regular expression. So A followed by any string having B's or C's. Okay, so we saw that this is the language recognized by this automata. All binary strings with an even number of ones, and the corresponding regular expression is this one, right? So, and the classic automata theory is wonderful, have beautiful properties, like it says that deterministic and non-deterministic finite state automata are equally expressive. Regular sets are closed under union, intersection, complement. And importantly, the emptiness problem and the language equivalence are decidable problems. You understand what a problem, what I mean when I say that a problem is decidable? So it means it can be, well, roughly speaking, solved by a computational means. Just a little question. Assuming that you have 2, how do you prove 3? Does anybody know? Well, a simple one. Why the emptiness problem is decidable? So you are given an automaton, and you have to decide if the automaton, the language of that automaton is the empty language or is not. How would you do it?
Which of you are from computer science? Quem quer de máquina? Você. Você tem máquina. Já fizeram na terceira, não fizeram?
So give me ideas. How would you look at the automaton, and how would you say, oh, this recognizes at least one sequence, therefore the language is not empty? How would you? Yes, exactly. If there is a path from any path from the initial state to the final state, and that's a simple algorithm in graphs, right? So far so good. Now we know how to do that, right? And how about the other one, language equivalence? You are given 2 automata this time, and you have to decide if the language is the same. A naive strategy that doesn't work is to try sequence by sequence. If you see if this is accepted, why this doesn't work? Yeah, exactly. Because it's an infinite set of sequence. So, but if you look at the second one, you realize that you can do the third one. Okay, I'll give you that as an exercise. The idea is like you can express the language, the equivalence to 2 sets using union, complement, or intersection. Then probably you can reduce the equivalence of 2 regular languages as a sum operation that's equal to the empty set. And since you can check that emptiness, we just see how, and then you can do it. Remember this property, number 2. But okay, we don't have time for that. So classic automata theory is solid, foundational, with several applications in computer science, parsing, for example. But it's not so good for reactive systems. Let's see a reactive system. This is a vending machine. So basically, you can press T, this button, or this button, and the idea is like the tea costs £2, and the coffee costs 4, right? So, and then you can use this automaton here to describe the behavior of this machine. You see. Now, let's suppose that all states are accepting, just for simplicity. The problem in automata theory is that you take this other B2, those 2 automata recognize exactly the same language. So for example, you take 2p, 4p coffee, you have it here, 2p coffee. Or you want 2p and then t, then you have 2p and t. So every sequence in one is in the other. So they are actually equivalent according to automata theory, right? But this one would be a very annoying vending machine, right? Actually, most vending machines are like that, but why this one here is very annoying? Why is not such a great machine, the one on the left? Exactly. Exactly. So that's the point. So this is a machine, and this is the point of interaction. It's a machine that you go 2 pounds, and you want tea? No, doesn't give you tea. You need to put 2 pounds, and then you don't get actually tea. You get coffee. And yeah, and will give you coffee and never tea, for example. It can go always like this. Tons of coffee and never tea. So the problem here is that this machine is the non-determinism. And non-determinism is used to express like the things that could go not wrong with the machine, but the thing that you don't know how they work. So what we need is an equivalence that will tell me, for example, these two are not equivalent. Because if I start interacting with this machine, they interact differently. Okay? So that could be the example. So first fact, language equivalence, the classic one that you know, is too weak for interactive behavior. It's okay for all the applications you have seen so far. It's still good, but not for this. But let's single out the actual problem. The problem is this rule in automata theory: A followed by B and C, plus C, sorry, is equivalent to A plus B plus, sorry, A followed by B plus A followed by C. You distribute there. And why you think this should not be equivalent? And it has to do with the vending machine. It has to do with what you said before. Yeah, exactly. Let's think in terms of football, since you guys are the best in football. So this is an A pass, and you make that A pass to this person. You pass the ball. And here you can do a B pass or a C pass. So you can decide if you pass it this way or you pass it that way, right? This one makes an A pass, but from here you can only pass this direction. You cannot return choose. So that's a good example why this should not be considered equivalent. Okay? So we need stronger and stronger equivalent that doesn't validate that kind of behavior. And this is what is called bisimilarity. Okay? So a label transition system is nothing but, think of them as like automata, where you don't care about initial or final states. So here's the notion of simulation first. You take a binary relation in states, and you say that this binary simulation is a simulation if for every pair, okay, the idea here is that it's called simulation because in this pair, Q is going to try to imitate what P does, okay? So if P does an action A and goes to some P prime, then Q can also find a Q prime, do exactly the same action, and stay in the simulation, meaning that this Q prime is going to continue simulating P prime. So that's the essential idea. Is that of simulation. You are simulating. You simulate another person, you can do whatever they do. If this makes a move, I can do exactly the same move. I continue imitating it. Okay? And the relation is, that's a simulation. And a relation is a bisimulation if R and its converse, R to the minus 1, are both simulations. Do you know what the converse is? It's like the same relation, but with the pairs inverted. Okay? So, and then we say now that P is simulated by Q, and you can find a simulation R that contains the pair. Okay? And P and Q are said to be bisimilar, and you write it like this, P bisimilar to Q, if there exists a bisimulation that contains the pair, right? Now let's go back here. Think of who is simulating what. P0 can simulate Q0. That's easy, right? Because if this guy does this A move, this guy does this A move, and now if this guy does B, you do B. If you started here, then you do A, and if you do C, you can choose here C. Can you tell me why is that Q0 cannot simulate P0?
While P0 can go move and then you can accept either of the inputs.
Perfect, yeah. That's it. So that's what you have here. I mean, formally you have to assume that there exists a simulation R that contains the pair and then get a contradiction with that, okay? That is not a simulation. But the intuition is the correct one. But you might think that this bisimilarity is too strong, that two things will be bisimilar if and only if the graphs are exactly the same or isomorphic. Now here, two graphs that they have different structure, yet they are bisimilar. How do you show that this P0 here is equivalent to Q0? Then you have to provide a simulation that contains P0 and Q0, and this is the one. You say, oh, sorry. So you show the bisimulation, and that's the bisimulation. So that's the beauty of this thing. In order to show that these things are bisimilar, you provide a bisimulation. It's like an invariant property. You have to come up with it. And let's check. So to be a bisimulation, you have to be, R needs to be a simulation, and R minus 1 needs to be a simulation. I'm going to show just one direction. So P0, for every transition of P0 does, Q0 must do something and remain in the simulation. Let's see. P0 does this A, goes to P1. Then Q0 can do A and goes to Q1. And in fact, indeed, P1 and Q1 are in the relation. So that one checks. Then you take the next one, P0 and Q2. So P0 is here. Okay, sorry, I forgot to check other cases. If P0 does this A here, there are only two transitions, this one and this one. If P0 does this A, you go to P2, and then Q0, okay, sorry, this one is with this, sorry, and Q0 does to Q1, and P2 and Q1 are in the simulation. So there you are. And then you check every pair, and then if they satisfy the condition, then you say they are bisimilar. Okay? So that's the strategy. You need to provide the bisimulation. So here's a question. Suppose that P simulates Q and Q simulates P. Are P and Q necessarily bisimilar? If P simulates Q and Q simulates P, are they bisimilar? Ah, sorry, I didn't know the word. I thought only the students on this side. 50-50. Democracy. Democracy. Who thinks yes and who thinks not? Yes, yes. And no? One no, one no. You don't count. Okay, so let's see.
Why?
Okay, so here's a. Say it again?
Because of these simulations, doesn't need to be one the air mining of the other.
Yes, exactly. Because one thing is, yeah, that's the best way to put it. I'm going to use the explanation. I'll show the contact example. Because to prove that P simulates Q, you find a simulation, let's call it S1. To prove that Q simulates P, you find a simulation, let's say S2. But S2 is not necessarily the converse of S1, so it's not necessarily a bisimulation. It's the same relation, but inverted, that you need to check. So and here is the nice counterexample. And also it shows that it's important to consider that. Consider these two processes, P and Q. P simulates Q, Q simulates P, and yet they are not bisimilar. Okay? And the trick is, we'll see this right now, but the trick is this one. This guy deadlocks. This one doesn't deadlock. So it's important not to be equivalent. Okay? But we'll see how we can easily prove this. But where are the mathematicians in the side? On that side? Okay, here is one. I'm gonna try to fix my definition. And I'm going to add another extra condition because that example was inspiring. So I'm going to go back to the example. Here the problem is that, for example, I make this move, this guy makes this move. When this guy does this guy cannot do that. I'm changing. So I'm going to add another condition to my bisimulation game. And I'm going to call it weird simulation. A weird simulation is exactly like a simulation, except for condition 2, which says, remember, this guy is the guy being simulated, and this is the guy simulating the other. Okay? The simulator and the simulated one. The second condition I require is that if the simulator does an A, then the P, the one being simulated, should also make an A move. Now, again, that's the question. Now I'm going to define weird bisimilarity. Oops. You say that P with this less than Q if there is a weird simulation that contains the pair. Same as before. And now you say that P and Q are weird bisimilar if you have P less than Q and Q less than P. So simulation in both weird simulations in both directions. The question is, could you find two processes that are weird bisimilar but not bisimilar? And you can answer, Katusha, that one. So find a counterexample when you say, look, okay, you can show this one, right? Notice that, remember that this P and Q are not bisimilar, but you can check that they are not weird bisimilar either. So this is a puzzle. Try to find two processes that are weird bisimilar, but not bisimilar. Okay? There is another way to look at bisimilarity, and is thinking of this as a game. So you have a game between an attacker called player 1 and a defender called player 2. And they are playing over this, trying to show, one is trying to show that P is bisimilar to Q, and the other one is trying to show that it's not. So the defender is trying to show that they are bisimilar. So the game goes as follows. The attacker must choose any valid transition from P or from Q. So he chooses. And that's the importance of bisimulation as opposed to simulation. You can choose from one state or the other. simulation, you start with 1. So he either chooses P, A goes to P prime, or a transition of the form Q goes in A to Q prime. Chooses. And now is the turn for the defender. The defender is trying to show that Q indeed can match that thing. So if the player 1 chose PA goes to P prime, then the player 2 must choose a transition of the form Q, A, Q prime. Okay? And then go back to the first step, and now your P is now P prime, and your Q is Q prime. And the other case in which the player 1 chooses instead this one, and then in that case the player 2 must choose P and imitate the move. That's the game. It's simple game. It's like I say I choose this, you choose that, and you try to imitate whatever I do. Okay? And then the players continue taking alternate turns until the player 2, the defender, is unable to find any valid transition to match the move of the player 1. In that case, the winner is player 1, because he found a way that I cannot imitate this game. Or the game reaches state PQ from which there are no transitions. There is no more to search for. Then in that case, player 2 wins, the defender, because it could defend all the moves that they were considered. Or the game goes forever. In that case, the defender also wins because he's always able to match the move.
In the first case, you prove that the two automatas are bicycles.
Uh-huh.
In the other two, you prove that they are. The first one proved that they're not.
Yes.
The other two, they are.
Yeah, exactly. It's like a game between you and I, and I'm trying to prove you. I'm trying to prove that they are bisimilar and you are not. So whenever you choose a match, I say, then I choose this one. And if I can imitate whatever you do, then they are bisimilar. No, actually, P is bisimilar to Q if and only if the player 2 has a winning strategy. Okay? So, huh? 20 minutes. Okay, so let's go here, then let's play this game. Who am I, the defender or the attacker? I'm the attacker, okay? So I'm gonna choose, okay, I know what to choose. I choose this one. What do you do? So if I choose this one, you can choose here or here. You say you take this one, right? And then I take this one. So you won, right? Okay, so let me try this way. I choose this one. So there's not much choice, huh? You have to choose here, right? And now it's my turn. And I'm gonna move to the other side, and then I choose B. What do you do? Nothing, because you are in this and you cannot choose, so I win. So that's the essence of the, and if I have, that's a winning strategy, and then I just prove that they are not bisimilar. Okay. Since I only have 20 minutes, I'm going to skip. I was planning to show you these properties. Bisimilarities and equivalence. And bisimilarity is itself a bisimulation, the largest one. Okay. That's bisimulation. Now we're going to move to the process calculus. So, as I said, process calculates much processes like the Lambda calculus treats computable functions. So that means that the structure of the terms represent the structure of processes. So this term, if I take P and Q are terms, the term P parallel Q represents the parallel composition of process P and Q. Q is not a bad word in Portuguese, is it?
No.
Okay, it's the Spanish version. Okay. Okay, I was a little worried. Okay, so and the operational semantics. Have you seen operational semantics before? Who has seen operational semantics? Okay, so logic. You have seen logic, right? So think of this as a proof system that tells me, like, if I can prove that P can make an alpha action and go to P prime, then I can prove that P parallel Q does alpha, it goes to P prime by Q, okay? That's from a proof perspective, proof theory perspective, but it's easier to think computationally speaking. You have these two processes running in parallel, P parallel Q, and P can do an alpha action and go into P prime. Then the whole system, P parallel Q, can do the same action, okay? That's what it's saying. So I'm going to skip this. Let's go to the semantics, to the syntax, sorry. So the syntax, now I'm going to talk about like think of it as a programming language, as a parallel programming language. It's more than that, or less than that. So the basic entities of the syntax are a set of n of A, B, C, which we call them names. And n bar is called the set of conames. For each A of this, there is an A bar over there. And the idea is that they complement each other. So there is a set of labels, which is the names plus the conames. And you label like L, L prime. And the set of actions are labels, that is name and conames, plus a particular distinguished action called the TOW or tau action, which is the unobservable action. In automata theory, it corresponds to is similar to the epsilon action. So it's something that you cannot see. If the system moves, but you don't see what it does. So it's an unobservable action. So this is called silent unobservable action. And as I said before, A and A bar are viewed as being complementary. That is, A bar bar is the same as A. Okay, this is the syntax. So my little programming language has the following. So a non-deterministic choice between a set of processes of the form alpha I followed by pi. I'm going to give an example of this, don't worry. P parallel Q. This is P running parallel with Q. This variable A, or name A, is local to P. Other people cannot see, it's like a local variable. And this one is like recursive definitions. I'm not going to care about it now. This is the way to define recursive processes, but it's not that important right now. So this is a summation, right? So if I write alpha.p, it's like with the summation when you have only one term in the sum, okay? And 0 denotes the empty summation, okay? And now we're going to see the intuition about that. And the set of all processes is called P. And here is the intuition, more or less, what the transition is. How much time I have? P does alpha and goes into Q means that P can offer an interaction with the environment via alpha and then behave as Q. The best way to see that is thinking of the vending machine. You have this vending machine, and if you try to press here, nothing happens, right? So this process does not offer this and this for interaction, but it does offer 2P, meaning that if somebody gives me two pounds, then I can evolve into a configuration where now I can press this button or press this one. Still, I cannot press this one. So these transitions it shows you the potential for interaction, okay? It's not like I'm performing an action. I'm saying that I could interact via this action alpha. So, more intuitions. It's a non-deterministic sum, so you choose one, or well, not you, but the environment. So this guy might offer interacting with any of these alpha I and evolving to pi, and all of the other options are cancelled. P parallel Q might offer an action from P for interaction, an action from Q, or if P and Q can communicate among themselves, so they can actually do a tau transition. That's what it arises. So this P parallel Q can either interact with the environment or among P and Q themselves. Okay, we're going to see an example. This one here may offer any action from P for interaction except the private one, the local one. This one is not because the user cannot see, the environment cannot see that action, okay? So here's a little example. You have AP running in parallel with A bar Q. So one possible is to do A and go into P and A bar Q. This is like you move on the on this side. And then there is the other one where you do AP parallel A bar Q, do A prime, and you evolve into that. You see? That is, this guy could like interact with the environment via A bar. But since this guy does A and this guy offers A bar, it's like they can interact. If one is sent, the other one is received. So it's a complementary action, for example. So they might synchronize via the tau action and go into P parallel Q. So there are the three possibilities. Okay? And from this little example here, can you see why the only possible transition here for this process, which is exactly this one except that you have restricted A? Why is that you don't have A or A bar here? Any ideas? Katusha? So the idea is that since this A is restricted, then you cannot interact with the environment, so you cannot offer A or A bar with that. So the only choice they have is to interact among themselves. Okay? So, and these are the rules, like in the logical. So, as I said before, the summation offers any action from one of the PIs and then evolves into a PI. The rest are forgotten. So, parallel composition can evolve from the left, from the right, or among themselves. So, if P goes into P prime doing L, and Q goes in L bar doing Q prime, then P parallel Q does tau and goes into P prime parallel Q prime. And this is the restriction. If P does alpha and goes into P prime, then restriction A, P can do alpha as well and goes into restriction A, P prime, provided that alpha is different from A or A bar. Okay, so that's the language. And 10 minutes? So this language is Turing expressive, meaning that you could encode any, for example, a counter machine, which is Turing expressive. And here's how you encode a counter. And the idea is to think of a counter as a box that you can interact with. So what is a counter? You have these 3 buttons. You can press the button to increase. You can press the button to decrease the counter, or to test if it's 0 or not. How do you know that it's not 0? You try to press the 0 button. If it doesn't, if it cannot be pressed, then it's not 0, for example. And an easy way to see that is the counter whose value is 0 is a counter that you could press 0 and stay in C0. Or if you press increase, then you go to C1. And Cn is a counter that holds n, and you can decrease and you go to Cn minus 1. Or you can increase and go to Cn plus 1. And then you can have your counters there. And if you have counters, sorry, there's a typo there, right? It's Cn plus 1. And of course, that will require an infinitely many definitions, but you can encode it with 2 definitions using restriction. I'm not going to explain this because it's a little complicated, but this uses a definition per each n. So it's infinitely many. But this is just 2, but uses restriction. So it means that restriction really, actually the most of the expressive power of this calculus is the restriction. Without restriction, it will not be Turing equivalent. So it's an important operator. Just a little question. Notice that we don't have P followed by Q, right? We don't have this common combinator. You do P first, and then you do Q. But the idea is that you could encode it. And how do you do that? Via protocol. So think that P is a process that when it's finished, it sends the action, I'm done, I'm finished. And then the other guy says, I'm waiting till the other is finished, and then I start. So that's the way you can implement this. So, and then you can define by similarity. So now you need to say when 2 processes are equivalent. And the idea is they are equivalent if their transition graphs are bisimilar. Take this process, for example. The process P, which does A and then B or C. That's a process that can be expressed in the language we said before. And its semantics is this transition graph here, right? So the states are the processes, and the transitions are given by the operational semantics that we just saw. And this is Q. And then, of course, we just saw that these 2 are not bisimilar. So now you have a way to compare the process of your language. And here there are many things that you can prove. I'm not going to have time to prove each one of them, but you might expect that P parallel Q should be bisimilar to Q parallel P, right? I mean, it's parallel composition. So basically, this rule says that it's commutative, associative, and 0 is the neutral element. Let's focus on this one. You think this one should be an equivalence? I mean, these 2 should be equivalent? You have P running in parallel with a process that have A restricted. I'm saying that that's equivalent like if you pull this A outside of the scope, and now it's A having P parallel Q under the scope. Yes, exactly. So this can be done if P doesn't have any occurrence of A. Otherwise, there would be a clashed OS names. And, well, the same for this one. I'm going to skip the proofs. But something I want to say that is very important is like, and this is fundamental. If you have an equivalence of processes, you want this equivalent to be a congruence. Do you know what a congruence is? Okay. Basically, what you want is that you can suppose that P1 is bisimilar to P2. Then you want to prove if P1 is bisimilar to P2, then you want P1 parallel Q to be bisimilar to P2 parallel Q. That means that you can replace equal by equals. And this is very important in software. If you prove that this program is equivalent to this other program, then you can replace one by the other in any context, and you don't change nothing. That's what congruence is telling me. And bisimilarity can be shown to be a congruence, and it's very easy to prove it, actually. 5? Okay. So let's skip the proof. So let's see something about logic, because how do you specify properties of this language? You use a model logic called the Hennessy-Miner logic, and just take any the propositional logic and you add the modalities. If you have negation, you actually only need one, right? So true, false, and these Boolean combinations are the same that you already know. And then there are these two. Diamond KF and box KF. And the intuition is, the first one is possibility. You say that a process P satisfies this formula if it's possible for P to do an action that belongs to K and evolve into a process Q that satisfies F. So basically this means it is possible to do something in K and evolve into something that satisfies F. Okay? And this is necessity. P satisfies this necessity if whenever you do an action, if P does an action that is here, then it must necessarily evolve into a Q that satisfies F. Okay? So, as an example, this formula, sorry, it should have been boxed here. It means that it's impossible to perform an action from this set. So, let's look at the semantics. Probably it's easier like this. So, okay, so P satisfies F1 and F2 if P satisfies F1 and P satisfies F2. And let's look at this one. P satisfies diamond KF if it is possible to find some Q such that P does alpha and goes into Q for some alpha that is in K, and Q satisfies F. And P satisfies box KF if whenever P does an action alpha and goes to Q, then this Q must satisfy F. So this is like a for all, and this is like an existential. Okay, there exists some Q, and this is for all Q that happens, that must happen. Okay. Here are some examples. This machine, the vending machine, satisfies the following. If you put 2 pounds, then the coffee button cannot be pressed, but the tea button can. This is what it's saying. So 2p, coffee goes to false, but it's possible to get tea. This one, it says, after, if you do 2 pounds and then 2 pounds, then you don't need to put more coins. I mean, you get into a state that you can only get coffee. Can you tell me what this could mean? Yeah, it is possible for B1 to get 2 pounds. Okay? So it's always possible to put a coin. So then we talk about the notion of distinguishing formula. The two guys that were not bisimilar, but the way a language equivalent, there is a formula that B1 satisfies that B2 doesn't. Can you tell me what formula is that one? Think of, for every transition of 2p, after doing a transition 2p, this one satisfies that it's possible to get t, right? Does this guy satisfy the same formula? The formula which of these two satisfy this formula? B1 or B2? Exactly. So there is a distinguishing formula. And then you can go and find distinguishing formulas for processes that are not, for this one too. For this one is the one on the right satisfies the property that it's always possible after doing A, doing B. Once you have done A, then it's possible to do B. Meaning, once you do A, it's possible. So the one that, whenever you do A, it is possible to do B. But this one doesn't satisfy that because it might deadlock. So this logic is very expressive. In fact, we conclude with this following beautiful, one of the most beautiful results in concurrency theory, that says that two processes are bisimilar if and only if they satisfy exactly the same formula. Or in other words, if they are not bisimilar, it must be possible to find a formula that tells them apart, meaning that one satisfies the formula and the other one doesn't. So that is a very interesting thing. So just summarizing what I showed you the notion and properties of bisimilarity, which is the main equivalence in concurrency theory. We talk about the CCS, this programming language for concurrency. And we talk about modal logic for specifying properties of concurrent systems. And we conclude saying that given a model characterization of bisimilarity, meaning that these two notions coincide somehow. And well, each time there are new things in concurrency theory, so this area keeps growing. For example, now one interesting thing is to look at social networks and how you can analyze them. That's like new challenges all the time. So you are welcome to join us. Thank you. You can send me if you find the solution to the puzzle I gave.
Oh, the weird.
Yeah, the weird by simulation. You can take a picture if you want. ¿Dónde está? ¿Dónde está? So those are the definitions, and the question is find two processes that are weird by similar, but not bisimilar. Okay? And you send it to Frank Valencia at okay? Don't Google me. Okay, thank you guys.
This is serious. Don't Google it. Você coloca Frank Valencia,
I have a terrible.
vai aparecer uma quantidade de povo que você não tem ideia.
How do you say tocayo? How do you say tocayo?
Ah, homônimo, né? Aí tem um monte de homônimo que é tudo. Tem um homônimo, né? Ele é porque ele é
So when she say that I have two jobs, it doesn't mean that my other job is that one, okay? So
de dia, professor, de noite.
thank you guys. It was a nice audience.